Thank you, all organizers -1. It's following Gerard. Okay. Okay. Yeah. Okay. Yeah. So I'll use the opportunity to be first speaker, so the blackboard is very clean. Yeah. And so I will speak about resurgence and what I recently understood about it. It will be really new, very simple examples which are not in textbooks. Yeah. So I'll start with some definition. Simple, I don't know, kind of linear resurgence package. It's a way to formulate some class of resurgent functions by Ekal. Suppose we have it's given by several data. So we have a collection of complex numbers. Maybe some of them could be repeated, some of them coincide. And the name for these numbers are singularities in Borel plane. This set could be finite or countable. So we start first with finite examples and go to countable. It's kind of first thing. The second object is for each alpha, the alpha, you have a formal series. Series, which I denote by I alpha formal, which is generating series, and variable I denote by Planck constant, and just to remind me that its small parameter goes to 0, and in quantum mechanical applications it's really Planck constant. And then third, it's collection, it's some divergent series which you want to summate. It's actually usually divergent. And the third thing, it's collection of numbers for any pair of distinct points, and these are called Stokes indices. Yeah, so usually they are integer, but in all examples which you today explain, they are integer. Yeah. So these things, and then that satisfies some compatibility property. So all things should talk to each other in a certain way. So the axiom, in fact, the full axiomatic is when you have infinitely many zeros, a bit more complicated. I'll imagine that I have finitely many, but the axiomatic is the following: it's there exists and then automatically unique collection of functions, actual functions of formal variable, alpha analytic of H bar. Okay, thank you. Okay. It's kind of analytic functions in H bar, but H bar should be sufficiently small, and argument of H bar is not equal to argument of any difference yeah, so the picture is the following. We have some collection of points, yeah, on a plane. These are singularities of my Borel plane. I take one of them. I can draw straight race, and it will be kind of put it at 0. It will be race when my function when functions will be have cuts. Yeah, so it will define in the complement on the cuts. If you have finitely many things, you get finitely many arrays, and function should be defined in each sector in neighborhood of 0. In fact, it should be defined in some kind of in slightly enlarged sectors should be, and extends through the boundary. So the boundary to a larger sector, and with the property and properties of the following. So get this bunch of functions for each alpha in many sectors, and in all sectors my functions E alpha analytic for the bar has asymptotic expansion at 0 given by this formal power series. So have the same formal power series expansion. And first guy and the second guy, what happens if you cross? You consider two adjacent sectors. The function extends a little bit on the overlap. In the overlap, what you get? You get two functions. You get functions, let's say, left and right, yeah? You get E alpha analytic H bar kind of right. It should be equal to this function on the left plus exponentially small correction. Sum over, in this picture I have Z alpha, and I have various maybe Z beta 1, Z beta 2, saying of this ray. I take sum over exponent minus Z beta I minus Z alpha divided by H bar, multiplied by N alpha beta I, and multiplied by E beta I analytic left. Yeah, so we get linear combination of with exponential small terms which do not affect formal power series expansion. Yeah, so we get actual functions and with the same formal power series. In fact, these functions, why they're unique, it's kind of clear because when you write this procedure, what you do, you have you glue some vector bundle. You have trivial vector bundle on sectors, and you make this gluing transformation across the overlap, and together you get it actually extends to 0 by Newlander-Nirenberg theorem. So you get holomorphic vector bundle, which is trivialized on sectors, and these things can be considered as holomorphic sections of this bundle, kind of coefficients in trivialization. Yeah.
Maxim, over what do you sum?
Over all beta I staying on this ray. Because I say that this rays correspond to rays coming from zeta I to other beta i's. Could be several of them. Yeah. So you get this holomorphic section, and holomorphic section is uniquely determined by its formal power series expansion. Yeah, so it's automatically unique. Yeah. So it's so that's a way to kind of, this will be resummation of divergence series. So how it's related to traditional approach? Maybe just write it here. Comparison with traditional definition of resurgence by Cal is the following. From these conditions, one can prove that, in fact, this series diverge factorially. C alpha k is less than k factorial times the constant to power k. so things are divergent, but what we can do? We can make divide by factorial, it's called Borel transform, and consider its expansion and write function on what's called usually zeta plane. It takes sum over c alpha k divided by k factorial, okay, 0 to infinity, zeta minus z alpha to power k. I take now convergent series, consider its expansion point z alpha, get a germ of holomorphic function. Yeah. So before I get my singularities, now I get the germs of holomorphic function. So I get many germs, and the picture is the following. If you make analytic continuation of these germs, then you can analytically make analytic continuation along any path which avoids this singularities in Borel plane. So it's automatically function has endless analytic continuation. Which was kind of axiomatic in standard approach to resurgence. It's just and then one can now do the following. One can draw the ray, straight ray, which avoids other points, and then we integrate. If we have some ray which avoids other points, what we can do? We make analytic continuation, integrate to going to some direction in certain angle theta, which is not forbidden angle. You make analytic continuation of this function multiplied by exponent minus zeta alpha divided by h bar. So make a kind of Laplace transform. And if you make Laplace transform term by term, you kill these factorials. You'll get a asymptotic expansion exactly this phi alpha.
Maxime, sorry.
Yeah.
I missed the condition which is for things that you cannot have k square or k factorial square. Why if the Jouvre index is less than 1?
It's it's all this, in this field simple linear. Yeah, of course there are larger classes of functions. It's kind of simplest class of resurgent series. Yeah, so you get this Jouvre index 1. Yeah, so you get these things, and this will be E alpha analytic in sector, and yes, that's how the standard procedure should make analytic continuation, make integral. Yeah, and by this way, in this situation, you get exactly this object which I described before.
What is the upper bound? E to the e theta?
Infinity plus infinity. Yeah, you go to some. Direction not on horizontal ray but straight ray. And what is the role of n alpha betas? The role of n alpha beta, it means that if you go from point z alpha to z beta, you have your function, yeah? You make analytic continuation, and then approach point z beta, you will meet some singularity. And singularity of this phi alpha zeta near ZB is the following. It's 1 over 2 pi I n alpha beta logarithm of z minus z beta times this phi beta plus holomorphic function. So you get the singular. So the jump will be exactly this function phi beta. So you get function if you go around. And take a difference, you get again holomorphic function which is phi beta. Yeah, so that's the picture, and this actually implies something very nice. One can see kind of numerically see this resurgence in very things. So suppose you have z alpha beta to the closest pair of singularities. So there's nothing to the alpha which closer to the beta, and let's say vice versa. Then if you make expansion at point the alpha, you have function with first singularities in the beta, yeah? You get this logarithm times something. And logarithm gives you automatically that the radius of convergence should be this difference between two functions. And moreover, one can see these terms for logarithm, because this will contribute to some growth of coefficient. And then you see the following. Then you get 2 pi I times z beta minus z alpha to power k over k factorial c alpha k. Yeah, so I get my c alpha k over k factorial are my coefficients of convergence functions, and I rescale to get radius of convergence 1. 2 pi I comes from this guy. You should have asymptotic expansion as k goes to infinity of the following form. It's n alpha beta multiplied by c beta 0 divided by k. Its contribution for logarithm multiplied by constant. Then consider logarithm multiplied by next term plus c beta 1 again k over k minus 1 plus etc. You get asymptotic series. And yeah, that's kind of major point. Yeah, actually conversely, yeah, so what you see is that this gross asymptotic expansion of large coefficients at series at one point is controlled by small coefficients at another point. The leading kind of term will be c beta 0, then c beta 1, and so on. And conversely, if the alpha is a closed point to the beta, you get the same effect if you can replace alpha beta. Then you deduce the following corollary. You take limit for k equal to infinity z beta minus z alpha to power k divided now by k minus 1 factorial, because it's k cancels with this guy, multiplied by c alpha k by c alpha 0, multiplied by limit you exchange role of alpha and beta. And maybe multiply also by 2 pi I squared, because it's also 1 2 pi I. You get this number. You take the product of numbers, multiply the 2 pi I squared is equal to n alpha beta times n beta alpha. And usually these things are antisymmetric. So it belongs to 0, minus 1, minus 4, minus 9. Yeah, so you get two series, and you calculate some limit for one, some limit for another, make product, and you get minus square of integer. Yeah, that's kind of manifestation of the resurgence. And one can see it in really basic examples. Okay. So what is geometric origin of such structure? It's very simple. You have, suppose you have, let's start with smooth algebraic variety. Complex numbers, and we get a function, kind of polynomial function, or it's in the one, and we get a volume element. This top degree, holomorphic top degree, algebraic top degree form, and this dimension of x. And I assume a couple of things. That first, f has isolated Morse singularities. So what does it mean? It gets some collection of points, find a collection of points such that f prime, which are critical points, derivative is 0, and Morse, it means the determinant of double prime is not 0. These things, and the second condition is technical. F has no singularities at infinity. I will say it by words, I will not write properly. You can compactify your variety by dividing this normal crossing, so that the map will be proper, and on each strata the vibration there's no critical points. So it's things like this, and then if you get such story, what is this simple resurgent package? You have z alphas are critical values. I'll write directly what are these analytic functions. They are the following one. You consider you have your critical point and put some Hermitian metric on your manifold and consider gradient flow for this real part of rotated your function. So you consider kind of something called Lefschetz-Timbal. It's kind of Rn embedded in your manifold, static at the point. It will be stable, unstable manifold for function rotated by some angle, real part of function rotated some angle. You need just only cycle of integration, and what you do, integrate exponent minus f of x divided by h bar by times volume of x. You get a convergent integral of this guy. This Lefschetz-Timbal project to straight ray under map f. So it will be like vanishing cycle, so you extend it by continuity this way, and then you correct it by leading term because it's it has z alpha divided by h bar, and also divide by square root of 2p h bar to power n. Its things come from leading term of the integral for h bar equals 0, and then you get function. And so it has some asymptotic expansion as h bar goes to 0, and asymptotic expansion you can calculate purely locally. It's kind of algebraic calculation. The leading term is the following. You can see the volume form at point p alpha and divide by square root of this determinant of second derivative at point p alpha. And you see, for example, if my variety is defined over q bar, x, f, and volume defined over q or q bar, then all expressions, all series which you get will be with algebraic coefficients. In fact, C0 alpha will have square root, but if you divide by C0, usually it has things less kind of more rational. You get usually get like square root multiplied by series with rational coefficients. Okay, and this n alpha beta are numbers of gradient lines coming from. We consider two Lefschetz-Timbals. And rotate them a little bit, consider number of intersection points, it will be n alpha beta. Yeah, so it has pretty clean topological definition. Okay. And kind of really concrete examples, one can do like this. Yeah, kind of the zeroth example is really the most basic one. X is just find space. The function is 1/2 sum of squares, and volume element is product of dxi. And then I get just one critical value is 0, and the series is just 1. There's nothing divergent about it. Yeah, so it's really you get just Gaussian integral. Then I can do something a bit more interesting. You get a fine line. Function is minus x plus x cubed over 3. And the volume element is dx. Then you get area integral, and critical points are z1, 2 are plus minus 2/3, and integral I1 is 1 over square root of 2, some over. Yeah, so you see that you get square root and some series with rational coefficients, as I promised. And I2, which is minus, it's the same, it's essentially the same series. You replace sign of h, and indices are maybe up to sign plus and minus 1. So it's area. And here's first Gaussian integral. And this next example is Bessel function. It's very similar. X will be c star. F will be x plus 1 over x. Volume will be dx over x. And critical points will be plus minus 2, suppose, and I1 will be again 1 over square root of 2. Sum over and indices are plus minus 2. Okay. Yeah, so that's these are elementary examples of the story, and one can generalize these things. Generalization is one can have instead of function on a variety, suppose have closed one form. Get closed one form. Let's say eta on x, and also the volume element. Then this form is not differential function, but one can go to some abelian cover, some universal cover. Some maybe go to x tilde some infinite cover, and f will be df will be pullback of my one form. Yeah. So what is the most simple example? You consider c star, x round c star, with coordinate x, small x, and a universal cover will be c with coordinate y. So x will be exponent of y, or y will be logarithm of x. You consider covering by logarithm, and my function will be exponent of y minus 1 minus y. So if you consider what is differential, it's again exponent of y minus 1 dy, and in terms of x will be algebraic one form. It will be x minus 1 dx over x. Yeah, so this will be form eta. Okay. And now you want to calculate this on this cover. You do draw again this Lefschetz symbols, and which will be copy of R, and you integrate. You make the integral, make asymptotic expansion, and what you see Stirling formula. So let's denote h will be inverse to integer n. Then you know n factorial over n to power n exponent minus n square root of 2 pi n. And usually people write its exponent of some series is Bernoulli numbers. I will just write exponent thing itself, so it will be 1 plus 1 over 12 h bar plus h square. And these are not Bernoulli numbers. Bernoulli numbers appear when you take logarithm of the series. Yeah, this is kind of bizarre numbers. First, it's rational numbers. Maybe you should multiply by something. I'm not sure. Maybe there are exists an encyclopedia of integer system. Yes. Yeah. This if you multiply, making them integer. Yeah. 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 I don't know how to call them. Stirling numbers. Stirling numbers, and what happens in this case? The set of this function on the universal cover has infinitely many critical points, and critical values is all integer multiple of 2 pi I. So you get 0, 2 pi I, minus 2 pi I, and so on. The series in this resurgent factors, all series and all points are the same. Are the same are exactly this Stirling series, yeah. And also, and stock synthesis is also very simple. Maybe I can explain you in a moment what will be the Riemann-Hilbert problem. By this story, it looks like you should have infinite dimensional bundle, but in fact it's not, because you have just one series, yeah? Here just one series, and what happens, you just have two analytic function with a cut on vertical direction, both up and down. You get function I analytic, I don't even put index here, I analytic kind of right, or maybe plus, and I analytic minus, yeah. You get two functions of h bar in right and left and right half plane, which extend a little bit to the overlap, which have the same asymptotic expansion, and it's given the following, like I analytic plus and h bar for real part of h bar bigger than 0 is exactly what we see here. I'll say something like this. It's kind of like gamma of s plus 1 divided by s to power s exponent minus s square root of 2 pi s at s equal to 1 over h bar. Yeah, so you get these things, and I analytic h bar for h bar, real part of h bar negative, is defined as 1 through the same things in the right half plane. You take same 6 but exchange numerator and denominator, and then one can see following relation, like I analytic minus of h bar, if you cross r plus, is equal to I analytic plus of h bar multiplied by 1 minus exponent minus 2 pi I of h bar. So it will be identity map plus some exponential small correction. It will just multiplication things. And similarly, if you cross array going down, you get I plus analytic h bar is equal to I minus analytic h bar. But now multiply by inverse series, which will be 1 plus exponent 2 pi I of h bar plus it's kind of geometric series, yeah. So here will be Stokes coefficients, will be minus 1 and 1, 1, 1, 1, 1. It will be Stokes coefficients. Okay. Now that's all very simple. Maybe I'll just remove this not interesting example. And now let's apply this this story, asymptotic of coefficients of series expanded to coefficients in two nearby zeros. Because here it will be the same series. Let's take coefficients at point 0. In fact, here there's a little bit more complicated situation because there are two zeros on the same distance. So you get two terms, and then one get the following formula. You get 2 pi. Yeah, I don't know this coefficients. I don't know by Stirling numbers. STK. Yeah, it will be these rational numbers, and the story will be the following. I take minus 2 pi I to power n. Oh, maybe what is it? K divided by k factorial. Stirling k has asymptotic expansion. K goes to infinity, and it there are kind of two different asymptotics for even and odd numbers, even and odd coefficients, and they're given by the following one. It will be 1 minus st0 Yeah, so you get such thing. It's kind of resurgence in the sense that you start with certain series. It has factorial. You correct this exponential factorial behavior. Look at this asymptotic behavior, expand in this negative powers essentially of k, and you get another series, and you see you get the same series. Yeah, so it's kind of like things reproduces itself. And it's actually very funny. If you look on this signs, then for odd k, odd large k, the asymptotic is given by Stirling 0, Stirling 2, Stirling with small even numbers, and vice versa. We take asymptotic for Stirling with even numbers. It's controlled by Stirling with odd. Yes. Yeah. Okay. So that's nice example, which is and this that it's kind of really yeah, from which you see really the first example from which you see this resurgence clearly. This numbers appears as asymptotic of themselves, and there was some generalization. Actually, there's a theorem, but it's a bit long to formulate. The whole story generalized. It works for arbitrary one form on algebraic variety, more or less. You get the same picture. Works for any one form, closed one form. And the position of singularities will be the following. You get finite collection collection of series corresponding to zeros of one form, and to get some numbers, and then all singularities will be this finite collection plus some lattice, Ct can see, and the lattice is given by a lattice of periods of my one form on algebraic variety. The M is embedded to C. It's actually first homology of my variety embedded mapped to C by integration of my one form. And this is kind of just the first very concrete example. And here's something really interesting happens. So you see that you get, for example, if my variety and function, everything is defined over number field, you get series over number field, but singularities are infinitely many singularities in the period of one form, of one-dimensional integrals. In the previous story, when I get algebraic variety, I have finitely many singularities, and position will be algebraic numbers. And here will be not algebraic numbers, will be kind of next level of transcendence. But series are always with algebraic coefficients. Yeah, so it's kind of next level after usual integrals. Yeah, now I'll just will be very briefly finish with things going to higher dimensions. One can go to makes examples of next level of complexity. We can see the R0 is 1, 1. You define sequence of rational functions, A0, A1, and so on. And you define through kind of iterated logarithmic derivative of x1 minus x, and you get something like called Euler polynomials. Yeah, for example, you get something like, I don't know, I'll write you A4 is equal to x times 1 plus 11x and this is, you get 24 permutations, and there's some kind of Euler polynomial counting drops and permutations. Yeah, there's some stuff. You get the sequence of rational functions. Then you define R0, R1 in other rational functions by the property that R0 plus R1, R0 to be 1. If you make geometric series, you get exponent of minus zeta minus 1 over 1 factorial A0, zeta minus 3 over 3 factorial A2. Yeah, so you get only even A's. Yeah, so you define some new polynomials, and then the property is like this. I'll just X. You get a completely similar behavior like for Stirling formula, and the function okay, yeah, what will be a resummation of divergent series? But in the story, it will be Fadeev quantum dilogarithm. Yeah, and yeah, that's and here the lattice is of rank 2. So the periods will be 2 pi I. This lattice Zm log x plus z times 2 pi I squared. So you see, you get numbers even of a larger complexity. They are two-dimensional integrals. Series have rational coefficients, like x is a rational number, or it's called actually parametric resurgence. It's not number, it even depends on polynomial and some parameter. And then you get things with two-dimensional integrals, and then this generalized more and more. One can have examples when you get a dilogarithm of non-trivial numbers appears as singularities. Again, finite collection of series. And this is kind of second level of complexity after the first one given by one form. And here we don't know even representation in terms of integral. It's open question whether one can write integral in this form. Yeah, so maybe I stop here. Yeah, okay, thank you.
We have a couple of minutes for questions.
Yeah.
Who is the second author of your theorem that you wrote here? No, you wrote here.
I think, yeah.
Cyberman.
Why?
Works for any.
No, second author.
Otto,
Cyberman.
Of
Cyberman.
NK plus.
Cyberman.
First line. First
Yeah.
line.
Jan Soebelman. It's my cursor.
Yeah. Okay.
Okay.
Soebelman?
Yeah.
Okay.
Okay, yeah. Sorry.
Yes. So at some time you mentioned that there was this graduation of rational, algebraic, and next level of transcendence and so on. But in fact, there is. So if you have a singularity which is something like alpha in the Puiseux series, you have some gamma of alpha which will appear in the expansion. So you divide it by this to get.
No, gamma appears when you get kind of non-integer monodromy, when you get fractional monodromy. It's another direction which, because my monodromy is integer, yeah.
Yes, but for example, in Stirling, it is kind of hidden in the square root of pi, which is a trace of a gamma of 1.
Yeah, it's true, yeah.
So I think that you have first to get rid of them, and then you get the kind that you are mentioning.
Yeah.
And also something which is, I don't know to which level it is generic, but for example, for the Stirling coefficients that you have, I prefer Stirling coefficients because Stirling number in combinatorics.
Okay, Stirling coefficients, okay, yeah. Okay.
Stirling coefficients. So in the book by Conte, you have some expression of them in terms of sums of, let's say, some type of permutations.
Yeah.
So they can be expressed in terms of combinatorial quantities.
Yeah, sure. Yeah.
And it's the case for many of those examples. As soon as the initial, let's say, geometric function has some type of meaning, the meta-asymptotics, which means the coefficients appearing in the asymptotics, have again some combinatorial meaning. And this is very astonishing.
Yeah.
And I don't know to which level it is generated, but there is too many examples so that it is just coincidence. So there is something to dig. And there is also something which is that quite often they satisfy some recurrences, which are a little bit like kind of quadratic sum over products and so on. And this also, I don't know what is the exact claim behind it. What is the exact type of recurrences that in full generality, those coefficients, they will satisfy. So I don't know if...
Yeah, I don't know, Yeah, here one can make, it goes beyond kind of holonomicity very much, yeah. You get infinite local systems,
This is clear. It's not holonomic, but however it satisfies recurrences, which are quadratic type.
Yeah, maybe. Okay. Okay, thank you.